Hey team, welcome back. We're doing another video on numerical integration. Recall from last time we talked about how they can be used to solve definite integrals. Today, we're going to talk about how they can be used to solve differential equations. If you're not familiar with differential equations, if you haven't studied them, first of all you will, but a differential equation is some equation that has derivatives in them. So here is y prime, the first derivative of y, and it's a function of the state. So it's a function of the state y itself. It could be a function of other variables x. It can also be a function of time. Now, why do we need to solve differential equations? Well, it turns out differential equations are all around us all the time. They in fact govern the behavior of most phenomena. So just a couple of examples. Dynamic equations of motion, for example. Here's an object, and here's an object in motion. The motion of that object is governed by differential equations. Next, Navier-Stokes equations. These are actually a whole system of really nasty partial differentials, and they're used in fluids. Stress equilibrium, so deformation of bodies. When I press on my cat tree, it actually deforms just a little bit, and that deformation leads to changes in stress, which leads to changes in deformation again. And also Newton's laws of cooling, so heat transfer and thermodynamics. Differential equations will govern the motion of thermal energy between materials and through surfaces. Let's define some terminology. First, there's the type of differential equation. There's ordinary and partial. You'll see these shortened to ODE, PDE, ordinary differential equation. In the equations themselves, the difference is a full derivative compared to a partial derivative. And where you'll find these, one example of ODE is in rigid body dynamics. One example of PDE would be flexible body dynamics. So I have an object in front of me and this object is compressible, right? It can change shape. That would be governed with a PDE. Other examples would be compressible systems, fluids, for example. Navier-Stokes equations are a system, a set of partial differential equations. PDEs are more difficult to solve. These are usually reserved for graduate studies. Today, we'll be talking about solutions to ODEs. Next, the order of the differential equation. When we say order, we're looking for a number. So first order, second order, third order, 12th order, something like that. What we're saying is look at the equation and then look at the derivative term. So in this first equation, we have ddt of y. So the first derivative of y with respect to time. This will be a first order differential equation because there is a single derivative. In the one below it, this is the second derivative of y with respect to time. This would be a second order differential equation. Underneath that, we have an equation with ddt of x and ddt of y. Now, each of these are first derivatives. Together, there's two of them. So this is also a second order differential equation. What if this x was the second derivative of x? Well, that makes two derivatives of x's and one derivative of y, so this becomes third. This would be a third order differential equation. Also, you can work with systems of differential equations. For example, what if we had this equation, the one on bottom, and then we combined it with another equation, let's say ddt of m and ddt of n, and this is some other function. We can say g, and this one is also a function of the states, m, n, and we could add m and n to the previous equation as well. Yeah. Now we can see that we have two equations, and these states are mixed. There's a cross correlation between these states. This is now a system of differential equations. The one on top, we're going to leave this one as is, so this is a third order differential equation on top. On bottom, this is a second order differential equation. Together, this set would be a fifth order differential equation. Now, for example, what are the orders of real-world systems? Again, Here's my eraser, I can throw it. When I throw this object, this eraser, it can occupy any position in space. It can also undergo any kind of arbitrary 3D rotation, right? It can occupy any orientation. This eraser, when it is in flight, is a 12th order system. We also need to talk about boundary conditions. If you're going to solve a differential equation, you have to have certain information ahead of time. That information could be about initial states, it could be about final states, so a target, or it could be a mix of the two, and you could have information about both boundaries. For example, suppose that we have two platforms, and the individuals on these platforms, they throw projectiles into the air. We know that depending on the height of the individuals, that's going to affect the trajectory of the projectile. So let's assume, I've drawn them left and right. Let's assume these two are aligned together. They throw their projectiles at the exact same speed and angles. We know then that the projectile cast from the lower platform, this one is going to come down, it's going to strike the ground. The projectile cast from the higher platform, this one will also come down and eventually strike the ground, but it is going to travel a larger distance. It's also going to hit a different maximum height. So the history of this projectile then is dependent on the initial height, the initial state. A final value problem, what if we had a target that we were trying to hit, and we need our projectile to strike this target? Now we have information about the final state of the problem, and then we could work backwards and we could sort out what height the platform needs to be in order to strike that target. Now, boundary value problems, these are very interesting. These crop up in, you can see them in controls problems and optimization problems. One example, suppose that here is planet Earth, and in some orbit around the planet, we have a satellite. There's our satellite. We want to move this satellite from its current orbit to a higher altitude. So we want to develop some trajectory such that it moves from low altitude to high altitude. That means that we have information about the initial state, we have the initial altitude, and we also are specifying the final altitude. And we now want to find this trajectory that gets it from here to there. So that would be a boundary value problem. Let's talk briefly about analytical solutions to differential equations. There are many techniques. I'm going to show you the easiest one today. It's called separation of variables. Now, we know that we're going to develop a numerical algorithm to solve the differential equation. We need something to compare it against. So let's do a simple example. ddt of y equals alpha y. Alpha is a constant, y is the state, and of course ddt of y, first derivative with respect to time. Now, when I say we want a solution to this equation, what we want is from this, we would like some equation for the history of y. At a certain moment in time, what is the value of y? At a different moment in time, what is the value of y? This is what we would like to recover, is some trajectory or history of the state y. Now, separation of variables, what we're going to do is we're going to take all of the y's and we're going to put them on the same side of the equal sign, and then we're going to move everything else to the other side. So what we can do is we can actually take the ddt, we can multiply both sides by ddt, and I can divide both sides by y. This is going to yield 1 over y dy equals alpha dt. We want to get rid of the derivatives, the d's. We want to get rid of dy and dt. So let's integrate both sides. If we integrate both sides of the equation, what are we going to have? Well, this becomes the integral of 1 over y dy. This is natural log of y. The integral of alpha dt is alpha t. Now, we also know that when you integrate, you're going to get integration constants. So I'm going to add, which side should we add the integration constant to? Well, what if we added it to both sides? What if I said plus C1 on the left and plus C2 on the right? Well, C1 and C2 are constants. So I could, just as soon as I do this, I could move the C2 to the other side, and we end up with C2 minus C1. Well, if C1 and C2 are constants, then C2 minus C1 is a constant. So we really just need one integration constant, and we can call that one C3, call it whatever we like. So we have natural log of y equals alpha t plus C3. What are we going to do next? Well, we said we want an equation for y, not an equation for the natural log of y. So we need to get rid of the natural log. So we will take both sides of the equation. We are going to take the exponent. So e raised to the natural log of y equals e to the alpha t plus C3. The left side of this equal sign, when you take natural log of y and you say e raised to that, really the e and the natural log are going to cancel, and this is going to equal y. What's going to happen on the right side? Well, there are some exponent rules that we can use. E to the alpha t plus C3, this is also equal to e to the alpha t multiplied by e to the C3. Okay, recall that e is just a number, 2.7. So it's a number, a constant raised to a constant. So e to the C3, that's also just a constant. So this equation then is going to simplify down. We can say that y as a function of time is equal to the e to the C3, let's call that another constant, and I'm just going to call it c this time. It's our final constant, c multiplied by e to the alpha t. And this is the solution to this differential equation. So given some value of time, you can plug it into this equation and you can get the value of y. Okay, so what we're going to do next is let's talk about a numerical approach to solving the same differential equation, and then we're going to have another video where we take the numerical approach and the analytical approach and we can compare them. In the past, when we've talked about functions, we've given explicit functions for the states. Y is a function of time. A major difference with differential equations, we don't have functions for the states. Now we have functions for the derivatives of the states. And those functions can themselves contain the values of the states. Which means this is why the initial conditions matter, because you put the initial condition into the equation and it affects the trajectory. Now those trajectories, we can look at them graphically. For example, if we do this with respect to time, we start at some initial time, we iterate through a series of times, and then we terminate at a final time, and we would like to develop or calculate this trajectory. So how should we approach this for developing a numerical algorithm? Well, we're actually going to go back to numerical differentiation. Recall that we can calculate or estimate the slope at a given point numerically. And we developed several algorithms for it. Let's go back to forward difference. The algorithm that we came up with for forward difference was this. ddt of y, which we're defining as f, so I'm just going to say f of y and t. This is approximately equal to y at n plus 1 minus y at n divided by. Now, we've called it h, and you can use h. You will also see delta t. Now, usually when we're doing differential equations with respect to time, we'll use a delta t. But again, it's the same idea. It's just your time step, your step size. Let's take this equation and we can actually solve this equation for the update. For y of n plus 1, just multiply both sides by delta t and then add the y in. So y of n plus 1 will equal y of n plus delta t multiplied by f of yt. Now, this, though simple, this is going to be our starting point for numerical integration of differential equations. This has a name. This is Euler's method. This equation, Euler's method, what does it mean and how do we use it? Suppose you're driving your car and you're in a particular position and you're going a certain speed. Remember the function fy of t, we have a function for the derivative. So you're in a place and you're traveling 60 miles an hour and you drive for 1 hour. Well, that means you went 60 miles. So your new location is your previous location plus the change, 60 miles. Let's put a specific equation in for the derivative. Let's say that ddt of y is equal to negative y divided by 2. And we're given some initial condition, and we're going to run it at a time step, a delta t of 1. First of all, let's characterize this differential equation. It's a full derivative, not a partial. That makes it an ODE, ordinary differential equation. Also, this is a first derivative, which makes this a first order ordinary differential equation. How many initial conditions do we need? Well, for a first order differential equation, you need 1 initial condition. If this was a second order, you would need 2. If it was a 10th order, you would need 10. So we're given 1 initial condition, so this will satisfy. Okay, let's take those numbers and let's put them into the equation, and let's just make a chart out of what happens. So on the first pass through the algorithm, the current value of yn is your initial condition, 10. We evaluate the function for the derivative, and we would say, well, negative 10 divided by 2, so negative 5. We take yn, we take f, and we calculate the update. So 10 plus 1 multiplied by negative 5, we get 5. This is the first pass of the algorithm. You write this algorithm in a loop, so it continues. Next time, the input value is 5, just copied from here. We calculate the slope again. This one is negative 2.5. We calculate the update. The update is 2.5, okay? Next pass. It comes in at 2.5. We calculate negative 1.25, and this one's new value is 1.25. You can see what's happening. With this differential equation, we can see that the system is halving, right? It's getting cut in half every time. From this pattern, we can see that it's never actually going to go to 0. It's never going to go negative. With this setup, this equation, all y is ever going to do as time approaches infinity, y is going to asymptotically approach 0 from this differential equation. So this differential equation is also a stable differential equation. And we will look at plots of stability and instability, unstable systems, when we do our screen cap video in MATLAB. Okay, so this is the algorithm that you have to implement in your homework. I will do another video where I talk about, where we'll look at putting this into code, and we will compare the performance of Euler's method versus that analytical solution that we did earlier. Also, we're going to have other videos on differential equations. We're going to look at more complex algorithms that will give us better answers than this, and we'll also look at higher order differential equations. Okay, that's it for this video. I will see you next time. Stay safe.